Hello again. Today we'll be continuing the topic of the phase plane analysis, and we will be speaking about how to apply the phase plane method for the general form of the dynamic system governing equation. Okay, let's write down the topic: phase plane analysis, and it will be about dynamic systems. I mean, we'll be speaking about the system which can be described by such an equation. I mean the x double dot and the right hand side in the form of the function and x and x dot. And like we stated last time, if we have such a form of the right hand side of our governing equation, then we are able to make some substitution. I mean, we are able to put that the x dot is v, and it causes that x double dot can be computed as a v dv over dx. And using that substitution, we are able to transform our problem from the second order differential equation to the system of two first order differential equation. It will be the first equation, and here we have the second equation. And using those two equations, we are able to analyze the dynamic of the entire system. And what is the advantage of that approach? In many cases, we are able to solve that equation separately to that form. I mean, the first step, we're able to find the relationship between the x and v, and then we are able to find the phase plane image of the problem. And in this next step, we will be looking for the time evolution of the displacement based on the v function. Okay, and last time we stated that, let's say, that part is a, let's say, first step. In the previous movies about the introduction to the phase plane analysis, we stated that in the next step we should look for some interesting point where the phase plane portrait has some special features. I mean, it will be the condition how to find the stationary points of our problem. I mean, we will be looking for the critical points where the right hand side of our governing equation will be 0. From the calculus we know that if the first derivative of the problem is 0, it means that we are dealing with the stationary point. Okay, using that condition, using that equation, we are able to determine some finite or infinite number of the x criticals, and in the next step we will be looking for some approximation of our right hand side of the governing equation. Why? Because there is a, let's say, quite wide class of the equation which we are able to solve based on the form of the right hand side of our equation of motion, but still we have a lot of problems where we are not able to determine the solution. And that is why, even if we're not able to find a solution, then we will be looking for the linearized form of our governing equation. In the general form, if we take the Taylor series expansion of our function, we know that the Taylor series expansion is, let's say, some way to express the function by the polynomial function. We are able to find such a description. If we take the Taylor series expansion in the neighborhood of the critical point, we are able to write down such a thing. I mean, there will be the constant term of our function, and the next step we have df over dx at x equals x critical and v equals 0. I mean, exactly at the critical point. And this argument here we have such a thing. And the second term, I mean the second first order term, it will be df over dv, again at the x critical and the v0, and times let's say, some linearization of the argument. I mean, in that case, it will be v minus 0. And of course, if we are talking about the Taylor series expansion of the multivariable function, we remember that there will be bigger number of the terms. But from the point of view of the linear analysis, I mean, from the point of view of the linearized governing equation form, it will be enough for us, okay? I mean, as some approximation, we will take only the first three components. And here we have important thing, because look, if we take the f at the point x critical and v 0, we see that it's our condition which was used for looking, I mean, for finding, for determining of the critical points. It means that if we are looking for the Taylor series expansion in the neighborhood of the critical point, we are able to eliminate that term. And that is why we are getting the simplified form, I mean df over dx at x critical v0 times x minus x critical and times, plus df over dv as second first order term v0 times v. Okay, here we have such a form, such an approximation of our right-hand side of our governing equation. Okay, and in the next step, because generally we are looking for some simplified phase image of our problem, it will be enough for us if we will introduce some, let's say, local coordinate frame. And we will do it by some substitution. I mean, we will substitute that our new frame, I mean the x tiled, will be given by shifted variable x. Okay, and what we have if we assume such a thing, I mean what we get if we assume that we will shift the x, then we are able to compute the velocity. I mean our new velocity, I mean the v tiled, it will be the x tiled dot from the, we know that fact from the mechanics, and from the other hand we see that it's given by that formula, I mean that it's a x dot. Of course, we have to compute also the derivative of the x critical, but it will be 0 because it's a constant value. It means that it's v. What does it mean? If we are looking for the simplified equation, I mean the linearized equation, there won't be any effect of the transformation of the coordinate frame if we are talking of v. There will be only the difference if we are talking about the x. I mean, we have the new function, let's say g of x tiled v tiled, which expressed the phase plane image phase plane portrait in the neighborhood of the critical point. I mean that equation gives us the information only about the phase plane image, but in the neighborhood of the critical point. Like the coordinate frame will be put it exactly at the critical point. Okay, and in that case, we have such a thing due to the Taylor series expansion of the multivariable function, and it is a df over dx. Important thing, we have to compute the partial derivatives based on our original form of our function. Okay, and times new variable x df over dv. Again, we have to take the old function f, x equals x critical, v equals 0, but we have to now use our new variable v tiled. Okay, and that equation will give us the phase plane image. Okay, and the last step, we can write down the simplified equation. It will be the v tiled times dv tiled over dx tiled equals gx tiled v tiled, which could be expressed or can be expressed as as that factor, let's say, I don't know, maybe a times x dot plus b v. Oh, sorry, not the dot, of course, a times x tilde plus b v tilde. And in many practical cases, that coefficient are termed in the different form. I mean, in practical application, we are calling that fit as omega square x tilde minus 2h times v tilde. Because it's, let's say, we can treat that thing as some equivalent damped harmonic oscillator, which will be similar to our governing equation, I mean to our dynamic system in the neighborhood of the critical point. Okay, let's consider some simple example. Okay, and we will consider such a case. I mean, it will be x double dot equals minus x times minus x x times parentheses 1 minus x. Let's consider such a simple problem. Okay, and let's do our steps from our algorithm. Okay, you will remember first step, it's to change the variable. I mean, we have the v dv over dx, and we have to put our right hand side. We see such a thing. The next step, it will be connected with the looking for of the critical points. I mean, our left hand side xv is exactly minus x1 minus x. In the next step, or maybe in other form, it will be minus x plus x squared. In the next step, we have to apply the condition for the critical points. It means that it will be right-hand side of our equation of motion will be exactly 0. It means that looking of that thing, we see that x times 1 minus x has to be 0. It means that we have the two critical, oh, sorry, let's put that indices here. I mean, it's 0. It means that x critical will be 0 or x critical will be minus 1. From the point of view of that equation, it means that for that simple case, we have two critical points. I mean, we'll have to find two. Linearized form of our governing equation. Second step, we have to compute the derivatives of the right-hand side due to our linearized form of governing equation. It means that we have to compute df over dx. What we'll get as a result? Due to that thing, we see that it will be minus 1 plus 2x. Second derivative, it will be df over dv. It will be constantly 0 because we see that our right-hand side does not depend on the velocity for that problem. And now we are able to compute it for our critical points. I mean, the for x critical equals 0, we see that the first component, I mean omega square, it will be minus omega square, because last time in our consideration we see that we assume that the a will be minus omega square. I mean, that component minus omega square will be exactly equal minus 1 plus 2x at point x equals 0. It means that it will be minus 1. It causes that omega square will be 1. From that point of view, 2h will be constantly 0. It means minus 2h will be constantly 0. It means that h is 0. Okay? For another critical point, I mean for the last critical point, we see that it will be exactly 1, like we computed. 1, and let's compute the values. It means that minus omega square, it will be minus 1 plus 2x at point x equals 1, it's, as we see, 1. If we're talking about that thing, it will be still 0 because we see that there isn't any connection between our df over dv with the x. Okay, I mean it's a constantly 0 as we see. And the last step, we have to write down the governing equation in the neighborhood of our critical point. I mean, for that case, it will be minus 1 times x, and it's 4x equals 0, x critical equals 0, for x critical equals 1, our phase plane image, it will be dv over dx. I mean the v tiled times dv tiled over dx tiled equals plus 1x tiled. What does it mean? It means that in the neighborhood of first critical point, we have such an equation and such a phase plane image due to the integration of that problem equals C. It means that it's a, let's say, family of the ellipses. If we are talking about that problem, we have such an linearized governing equation and here we have such a solution. Oh, I forgot, due to the integration, I forgot about the square, and it will be another constant of the integration, d. I mean, if we are talking about the xv, if we are talking about the first critical point, we have the family of the ellipses, because it's an equation of the ellipse. If we are talking about the second critical point, I mean if we are talking about the one, here we have the family of the hyperbolas, and that kind of the point is called saddle point. Okay, and here we have the indicators of the process direction. Okay, as you see, even if we have some nonlinear problem, nonlinear governing equation, we are able to make some simplified analysis of our case, and using linearized form we are able to find the solution and draw the phase plane portrait of our dynamic system. Thank you for your attention and see you next time.